My name is Stephen Heitch, and this is my Lab 3 on black holes and orbits. So for our general outline, we will look at an introduction, we'll look at the main physics principles, the code and predictions, our comparisons, errors, and some general results. So for our introduction, the purpose is to understand orbital motion and to be able to find the mass of the black hole that we do not know given the motion of the star that we do know about. Our main concepts are Newton's second law, the global force of gravity, and we'll use the glow script of a black hole and the planet, and a second glow script of a planet, the moon, and the spaceship for our experiments. And what we find is that we couldn't get the computer to make a figure-8 orbit, but we did find that the mass of the black hole was about 5.6 times 10 to the 43 kilograms. So for our main physics principles, there should be no forces other than gravity. So we're kind of ignoring anything else that there could be theoretically and only focusing on the things that we are told are there. Newton's second law, again, that the final momentum equals the initial plus the force times the time. So we divide all this by mass, we get our velocities, we use the velocity, and we can update our position. Again, using that, our final velocity will be approximately our average velocity for the non-constant force. Gravity, we know that it's always given by the equation negative g m1 m2 over r squared r hat. So we can always rearrange this if we just take the magnitude of it. We can always find that the mass of mass 1 is equal to the force r squared over g of the mass 2. Again, we're assuming there's no other forces. So for the code and predictions themselves, what we did for the black hole was we took the randomly generated initial conditions, so it'll give us our initial positions and velocities and everything else, and then we will cycle through all the positions it gives us and calculate the mass of the black hole based on the observed change in momentum at each position. So we look at how it changes, and then we can calculate the mass of the black hole at all of the different positions, and they will be a little different, and at the end we average them together. So this is the code of it running. The magenta arrow is the direction of travel, the blue arrow is the normal direction, and the orange arrow is the direction of the force of gravity. So for the second one, the planet, moon, and ship model, we set the initial speeds of the ship randomly. The initial conditions of the moon were set by the program. And then we tried a lot of different speeds to get a figure-8 orbit. We didn't get one, but that's all right. And the code was just told to iterate and update the object's position and force at each time step. So it was done very simply. Again, we just calculate the gravity with the g m over r squared r hat formula to get the gravity on everything, and then we move it using Newton's laws in the standard way. So this is the first output we got, or one of the outputs we got, where it moves around. You can see it's orbiting, and as it moves, the moon shifts the direction that the orbit is facing. Again, not a figure-8, but you can tell that it's affected by both the moon and the planet. This one is kind of similar in the sense that you can tell it's affected, but it is not a figure-8. It orbits around to get shot out by the moon, and as it comes back in here, it blips back out towards a different orbit, again, because the moon forced it to do so. So what does it mean? If we're looking at the rate of change of momentum and comparing it to the net force, they are the same thing for the most part. The only difference is we can measure the rate of change of momentum just based on looking at how fast it's going at a certain place and where it is and how much it weighs, so we can calculate that. Whereas the net force is the sum of all forces, so we can get it by looking at the rate of change of momentum, but we can't necessarily know what makes it up because it's made up of a lot of things and things can cancel out, so you never really know they're there. And for both of them, the parallel component, or the component in the direction of motion, affects speeding up or slowing down of the object, and then anything perpendicular to the direction of motion affects the turning of the object. So to include all of these things together in our planetary model, we would also have to include the black hole and the star, and the black hole would drive the whole thing. The force of it would create the main motion around everything, and then the motion of the moon around the planet on its path, it would all be controlled by the black hole, generally speaking. So some errors that we've probably got, because FNet is not a perfect representation of the force over the time delta t, if delta t is more than dt or 0, there is some error due to that. It's not a perfect representation of the force. And that's the same with the final velocity being used. If if delta t is bigger than dt, then the final velocity will not perfectly map it, but it will give a close approximation. Found that the average mass for the black hole was 5.6 times 10 to the 43 kilograms. And for the second model, we could not get a figure 8 motion, but if we could figure out a way to calculate what it would require, then we could find one.